All right, gang, let's talk about the 802.11a wireless standard. Now, this thing goes back to 1999, so you're thinking to yourself, wow, how old and slow is this thing? Is this a decrepit geezer? Well, actually, not bad. It operates at 54 megabits per second, the same thing that it took till 2003 to get with 802.11g. So why, in fact, did we have an 802.11g standard when we already had something that was 54 megabits per second operating using orthogonal frequency division multiplexing, OFDM? And the answer is it was defined at the 5 gigahertz frequency. So it was not interoperable with B. It was a beta and VHX. It was a PlayStation versus Xbox scenario, right? Two different configurations, not compatible with each other, both doing the same thing. The higher frequency allows us to more consistently be able to send that data at that high speed. The frequency itself is helping to lend to a higher data rate. But the downside of 802.11a, especially as it was originally conceived back in 1999, is the fact that this standard was very susceptible to interference. That higher frequency deals with the fact that you can have more challenges. You have loss of signal over a shorter period of time. So free path loss is increased, and penetration of signal through different surfaces is also going to be more of a challenge. So what we ran into was 802.11a would work really well for certain scenarios where I had a short distance. In that short distance, it might actually do better than 802.11b at having a high degree of signal strength. So shorter distance, again, sometimes industrial high-speed needs could be satisfied with this. Again, at the 5 gigahertz range, there's 24 US channels that are available, and according to the European standard, there are 19 channels that are available. Again, DFS and DPC, both referring to the control of those signals as they might interfere with Doppler radar. Again, DFS and DPC dealing with the dynamic frequency selection, and then the power control that's associated with dialing down the power or changing frequencies dynamically so as not to interfere with the other important things like Doppler radar that operate at the 5 gigahertz range. So those are some components that we see here. Again, here's a look again. Just remember that when we're operating at the 5 gigahertz range, these frequencies look completely different than the channels that were used for the frequencies in 802.11g. Let's revisit G and B. Right, 22 megahertz wide, and just notice this overarching band that's using the whole signal range and tons of overlap with adjacent signals. When we get an 802.11a and other things that operate at the 5 gigahertz range, things get a lot different because now we have these 20 megahertz blocks in terms of separation. So there's this 20 megahertz range right here. There's a little bit of gap space here between that and the next one. So again, 20 megahertz for our frequencies that we're working with. And there's actually multiple bands. We have what are known as the Uni 1, 2, and 2 extended that are all available for indoor or indoor-outdoor use in the case of 2E for selecting those particular ranges. So we can call upon these frequencies at these different channels. Let's see, anything else here? Yep, here we go. So again, in terms of the data rates, the maximum data rate supported by 802.11a at the 5 gigahertz range is 54 megabits per second. Why? Because it's using OFDM, orthogonal frequency division multiplexing, with a 20 megahertz channel using 64 QAM as its modulation, as its most advanced form of modulation. So across all the different subchannels that are operating within any one of those 20 megahertz channels, we can push out this many kilobits per second. So again, works its way down 54, 36, 24, 18, 12, 9, and 6. Notice it does not have those really low end Barker mechanisms of 1 and 2 megabits per second. Doesn't play that game because those are direct sequence spread spectrum technologies. Doesn't touch those at all in 802.11a.